The next topic is models and parameters. So this one can be a little tricky, so I will try not to go too quickly. We will start with this silly cartoon that I have drawn. So I think of models as kind of like cartoon machines. They're machines that take inputs and convert those inputs to an output. In our class with statistics, with early statistics, we might have several different kinds of input that go into our model, but our model will only have one output. They're univariate. So these models are imaginary machines that do that. So these inputs might be like what group someone belongs to, or their height or weight or something like this, and then this might be their shoe size or something like that. And our machine is trying to estimate what the predicted shoe size is based on the inputs. In addition to these raw inputs, a machine might also have some settings that you can tweak to try and affect exactly how the inputs get turned into the output. And when we're talking about models, the equivalents for those settings are the parameters. So move on from the picture here to something a little bit more boring, but maybe more concrete. So one of the things that can help you understand models is thinking about processes and patterns. So when I talk about a process, there are some real world phenomena that are processes, that they generate data. Games of chance, customer behavior, weather, anything in life that generates observable phenomena, we can call that a process. And those observations that go with them are data. Observations of variables grouped into samples. So that's one kind of pattern we can observe, is data. Another kind of process is a mathematical model. So functions and formulas that describe how one input might get turned into an output. And then probability distributions or patterns, those can describe our expected proportion of all the different kinds of outcomes that might occur. So one thing that's different in statistical models from maybe like a classic machine is that there's often a little bit of noise or variation in the output. You could think of it as a machine that's not perfectly calibrated so that there's variety in how the outputs are produced. Let's go back to our silly cartoon, my silly cartoon. No, wait, we won't. We'll talk about data first. So we talked about data before as a pattern. And when we're dealing with stats, those data play two roles. First, I want you to think about the output. So in our class, we're going to have one column, one variable in our data set that will be an output variable. And it's usually continuous. And when we're doing our statistical analysis, what we're usually trying to do is predict the value of that variable. So to guess what, if we collected some new data, to be able to predict what that new variable would be. And so that output variable is often called the dependent variable, because its value depends on us carrying out an experiment and looking at how the other variables affect that prediction. And sometimes it's called the response variable because we're performing some kind of experiment or we're running the model and we want to see how that particular measurable quantity responds to the environment that we're exposing our subjects to. So dependent variable or response, those are outputs. If a variable is not an output variable, then it must be an input variable. So all variables are either output or input. They can't be both in this course. So we might have one variable or we might have multiple input variables when we're doing our analysis. Typically we'll only have one variable. And input variables can either be continuous or discrete. We will look at cases with both of them. And whether the input variable is continuous or discrete is an important factor that we use in deciding what particular mathematical model, what probability distributions we're going to use to try to understand the noisy part of our data. We call these variables independent variables often because when we're setting up an experiment, we decide what those are going to be before we've even run the experiment. So we might say we'll make 10 phone calls or 20 phone calls or 30 phone calls as part of our telemarketing experiment to see what the most effective way of reaching out to potential customers is. You will also hear input variables called factors or effects because they influence the output variable, the value of that output variable. So those are the two roles that data can play. So going back to my silly picture, data are over here. There's inputs in our data, and there are outputs in our data. And what we don't know from the observations are the parameters of our model. So we're going to try to figure out, we say, okay, we think this machine, let's say like a Bernoulli process for modeling a coin flip, or a normal distribution for modeling people's heights or something like that. We're going to say, we'll decide what kind of machine we think is running, and then based on the relationship between our inputs and our outputs, we will guess about what the parameters of that model are. And moving away from the cartoon, we usually represent these models as equations. So we say that the output variable, the response, is equal to the sum of these different effects. One or more, it would be, in this case I have 3 plus the noise. It could be more than 3, it could be less than 3, it could just be 1. So here's two examples. If we have measurements of a whole bunch of people's heights, then we also have the parents' heights, and some description of what kind of diet they grew up on. We might expect that the parents' heights plus the diet would give us a guess about what a person's height probably is, and then the observed heights would also vary around that by some normally distributed noise. Likewise, if we were doing some kind of taste testing of ice cream sweetness or quality control of ice cream sweetness, so we wanted to know how sweet a particular batch of ice cream was, we might expect different flavors of ice cream to affect that sweetness. And so then each flavor would have its own effect. And then as the sugar content increased, we might expect the ice cream sweetness to increase. And as the fat content changed, we might also expect that to change sweetness. Maybe the fat would coat your tongue and things would seem less sweet. And then again, there would be some randomness as well. So in the height example, we've got 3 inputs. Oh goodness, that's flavor. I forgot to change the title. Hilarious. Well, I will change this to, here, let me just do that right now. Sweetness equals flavor plus sugar plus fat plus noise. There. Very professional. Outstanding. So we would expect, so one input would be flavor, and a parameter associated with that would be different flavors would have different sweetnesses associated with them. We might think chocolate and strawberry might make something seem sweeter than vanilla by itself. Maybe less. I don't know. Sugar content is another input. We might expect there to be, if we measure the sugar content in a continuous way, we might our parameter would be a slope, that as sugar increased, the sweetness rating increased. And then fat content is another input. We might measure the fat content, and maybe we expect as the fat content increases, sugar content, the sweetness rating decreases. And then finally, another parameter that we could estimate would be the average sweetness rating for all of the ice cream. So we end up getting one parameter for each flavor, and then this sweet slope with sugar and the slope with fat, and average sweetness. So depending on how many flavors we have, we could have like 10 or 11 parameters. That's hilarious. Okay, let me fix that then too. Good times. So again, if we have parents' height, that's going to be a continuous variable. We expect people with taller parents to be taller themselves. So that might be a positive slope. That parameter we're going to estimate how tall you are based on your parents' height. But it's going to be a guess, and people will be variable around that. And we expect diet to affect that too. So if you got like tons and tons of food growing up, probably got taller than someone who was only getting a little bit of food, sort of get by food but not too much excess. And then someone who's in famine, they're probably going to be shorter than average height than you'd expect from their parents' height. So we could estimate the effects of those 3 different levels of diet, and those would be parameters in our model. And so the next question that I'm going to cover now that I've talked for 10 minutes is how we choose parameters. And that is the next